This video presents a complete exploration of the zeolitic imidazolite framework ZIF-62, beginning with the fundamental principles of metal-organic frameworks and progressing towards their practical industrial applications. We follow a synthetic roadmap starting from commonly available reagents and advancing to the specialized organic linkers required for the construction of the framework. ZIF-62 is a mixed linker metal-organic framework composed of tetrahedral zinc-2 ions coordinated by imidazolate and benzimidazolate linkers. Unlike most porous crystalline materials, ZIF-62 melts concurrently at approximately 437 degrees and can be quenched into a stable amorphous glass called Ag ZIF-62. The resulting pore distribution makes this material particularly promising for CO2 molecular separation as we use it. Metal-organic frameworks were recognized with the 2025 Nobel Prize in Chemistry, highlighting the transformative potential of this field. In addition to experimental synthesis, this work provides a digitally optimized ZIF-62 crystal structure prepared for computational studies. Using this structure, molecular dynamic simulations, including melt-quench protocols, are performed to investigate how different process parameters influence crystal-to-glass transformation. Finally, additional analyses are conducted to characterize the structural and functional properties of the resulting amorphous material, but more of that later in the video.
Metal-organic frameworks, MOFs for short, are a class of materials built like molecular scaffolding. They consist of metal atoms connected by organic linkers to form highly ordered, three-dimensional structures that repeat indefinitely in space. Try to visualize it as a higher class of polymers. What makes them special is their extreme porosity, as at nanoscale MOFs look and act like sponges for molecules or in some cases even atoms, and these unique interactions is what is of interest to modern-day chemists. MOFs are currently being explored for a wide range of applications, from gas storage and carbon capture to catalysis, drug delivery, high-performance electrodes, and even water purification. Their key advantage over pretty much any other material is their flexibility, as by changing the metal ions, the nodes of the MOF, or the linkers, the organic connectors that link the nodes together, you can design a material with very specific properties built specifically for what you have designed it, because you can control the size and chemical properties of the MOF you create. One MOF of particular interest is ZIF-62, which is part of the zeolitic imidazolite framework family, which very closely resembles the structure of zeolitic rocks in nature. It combines zinc with the organic ligands imidazole and benzimidazole, forming a structure that is both stable and versatile, and slightly more, let's say, disordered than other MOFs due to it having mixed linkers. What sets ZIF-62 apart is its ability to exist not only as a crystal but also a glass. When melted and rapidly cooled, it forms an amorphous structure while preserving much of its chemical functionality. This opens the door to new processing methods and industrial applications, especially in gas separation and CO2 capture, where understanding how structure affects performance becomes critical. In this video, we'll explore how both experiments and simulations help us understand and optimize materials like ZIF-62.
So, moving away from the theoretical and entering the practical field. Now we go into the synthesis, and first we're making imidazole by the Debus-Radziszewski condensation. The overall reaction combines glyoxal, formaldehyde, and ammonia, producing imidazole and water as the only formal byproduct. Mechanistically, glyoxal reacts with ammonia to form the imine intermediate. Keeping the mixture cold here is critical, because at below 10 degrees Celsius, the diimine formation happens quickly, while some unwanted polymerization reactions need more activation energy. In other words, the cold temperatures, as in our fridge, bias the chemistry towards the products we actually want instead of the brown mystery goo, which unfortunately still ended up compromising our project. Once the diimine forms, it reacts with the formaldehyde to generate an amino alcohol intermediate. That intermediate cyclizes, forming a dihydroimidazole ring, and then dehydration plus taumerization aromatizes the system into imidazole. After slowly adding ammonia and letting the reaction stir overnight, first in a cold environment, then at room temperature, the solution darkens slightly. Purification should have mostly been acid-base chemistry, as acidifying the mixture with hydrochloric acid would have turned the imidazole into the water-soluble imidazolam salt, and any organic impurities would have been extracted away with the dichloromethane, and then basification with sodium hydroxide would have turned everything back to normal. Luckily, the solubilities of the two are very different, and imidazole can dissolve in cold ethanol, whereas salt does not. So water is evaporated, and then ethanol is used to extract only the pure imidazole. The reactions had mostly been theoretical. In order to battle that, we ordered a lot of glyoxal in November. However, even today, as we are recording the video, the Glioxo has still not arrived, so unfortunately we weren't able to conduct sufficient trials, and unfortunately our imidazole synthesis were sabotaged. The next synthesis is benzimidazole, which looks just as it sounds, a benzene ring connected to an imidazole ring. We're making it using the Phillips condensation, a reaction where O-phenyldiamine, or OPD, reacts with formic acid under strongly acidic conditions to form benzimidazole and water. Mechanistically, the chemistry happens in two temperature-dependent stages. At low temperature, one of OPD's amino groups attacks the protonated formic acid, forming a monoformamide intermediate. Then the interesting part happens at around 90 to 95 degrees Celsius. You get it to almost boiling point, but you don't go over the threshold. It is when the second amine now attacks intramolecularly, closing the ring. And after losing water, it turns into the thermodynamically stable benzimidazole. The purification relies almost entirely on acid-base solubility control. Under acidic conditions, benzimidazole exists as a protonated benzimidazolium ion and dissolves extremely well in water. Once we raise the pH with sodium hydroxide to about 13, it converts to the nitro-free base, which has very low aqueous solubility. Then, instead of filtering directly, we exploit partition chemistry. Nitrobenzimidazole is much more soluble in dichloromethane, or DCM, than in water. So repeated DCM extractions transfer nearly all of the product into the organic phase, while inorganic salts and polar byproducts stay behind. After evaporating the solvent, we obtain some pale crystals, which in our case had a bit of brown, which turned out not to be a problem. Purity is especially important here, because leftover OPD strongly coordinates zinc ions and can disrupt the ZIF-62 crystallization. So in order to verify our product, the only method we had was testing a melting point, and it was expected to be at around 165 to 170 degrees, and in our luck, it turned to be exactly that. With both imidazole and benzimidazole prepared, the goal was to synthesize ZIF-62. Formed when zinc self-assembles with the deprotonated linkers in hot DMF. At elevated temperature, DMF partially decomposes to produce dimethylamine, which acts as a weak base and activates the linkers for coordination. Ideally, this leads to the zinc-nitrogen bonding and growth of the ZIF-62 crystals. In practice, things absolutely didn't go that smoothly. The imidazole contained a lot of significant amount of byproducts, which likely interfered with the coordination and prevented proper crystal formation. Instead of well-defined crystal, the reaction produced a dark charred sponge-like solid, which was very hard. The situation was complicated for further equipment limitations. Our microwave reactor had no precise temperature control, as it was just an old Soviet microwave, so heating had to be manually adjusted throughout the run to avoid combustion and, explosions. Because of limited laboratory resources, the synthesis couldn't be repeated, so at this stage we can neither confirm nor deny the presence of the ZIF-62 in the final material. For future reactions, we want to turn the ZIF-62 into the amorphous glass ZIF-62. However, in our conditions, that is currently not possible.
To begin with the computational side of our work, we first need a valid ZIF-62 structure. Crystallographers share this information in the form of .cif files, which mainly explains how the structure looks and how it repeats in space. Due to ZIF-62 not being as explored as other MOFs, finding a file that was usable for geometric optimizations proved to be harder than expected, as most had solvent molecules present and were extracted from experimental data. We finally settled on Gandhara Wall, sorry if I mispronounce it, and her team structure used for gas separation simulations, which saved us the agony of creating the MOF manually. The file, however, was still not perfect for our use as it wasn't geometrically optimized. To optimize such a structure means to minimize the forces present in the system. The structure had almost 2 right per bore of force present, which is roughly 10,000 times more than what would be sensible for us to use in our later melt quench simulations, so we had to change that. To understand geometric optimization, we first need to talk about density functional theory, which was probably the biggest breakthrough in computational chemistry and material science. In quantum mechanics, if you want to describe a system of many electrons exactly, you would in principle need to solve the full many electron Schrödinger using the Hamiltonian operator that represents the total energy present in the system. And that is the equation, where the upside down triangles, the nabla, represent the kinetic energy of each electron, VR1 and VR2 the potential of each electron, and VR12 the potential energy due to the repulsive forces between the electrons. Now, when each of these terms needs to be calculated, which include very computationally expensive operations, that becomes insensible for the computer, so something needs to change. As also, keep in mind that system of only 2 electrons, that's a helium atom. In our case, we have more than 300 atoms with electron count of roughly 2000. That not only interact with the neighbor same atom electrons, but also with the rest of the system's electrons. It becomes impossible. DFT changes the question, as instead of having the computational calls grow exponentially, thus the electron-electron interactions, it grows only cubically by using a much simpler term than a wave function called the electron density. And the brilliancy of this reduction is that it is lossless in terms of accuracy, it's exact. There are problems with it still, but that's topic for another time. Electron density is still defined by wave functions, but reduces the problems of thinking about every electron individually to thinking of them as a whole system, so we only have 3 dimensions to work with instead of the 3 n dimensions before. The electron density becomes valuable because of the theorems of DFT coined by Kohn and Honenberg, where A, the ground state, the minimal energy of the system, is a unique functional of the electron density, so therefore B, the function of the electron density that minimizes the overall energy, is the ground state of the electron density. The energy functional, on the other hand, consists of the sum of the total energy due to Coulombic interactions and the exchange correlation functional, which is the thing DFT is going to try to approximate in order to minimize the energy via the electron density. That functional is the heart of quantum mechanical interactions and preserves the ab initio accuracy of the model. So DFT now will try to solve the ground state by the Kohn-Sham equations. It would begin by guessing an electron density, based on which it would solve the Kohn-Sham equations for each electron by putting it in the Hartree product, which is the energy of the electron coming from it being in the field of electrons, and finding then the single electron wave functions of each electron. Then, remember how the electron's density standard definition is the product of all wave functions for each electron? So we calculate the electron density and compare it to the one we've guessed in the beginning. If it is the same not meaning exact but extremely close, then we reach the ground state. If not, we are not yet at ground state, so we make a new guess and cycle like that until we get the same electron density. Something which was hard for me to understand was why when I guess a value for the electron density and then use it to calculate the wave function and then use the wave functions I got to recalculate the electron density, I usually got a different answer. The thing is that these operations are not linear. It is more of solving a function based on the result of another function that are independent of one another. In the most simple way possible, we solve an electric field in the Hartree product using the electron density added to the whole energy of the system, based on which we calculate the wave functions, which are the thing that represents how the electrons would actually react within such a field of energy potential. Then, the electron density we get from the wave functions is not determined to equal the one we guessed, because the electrons will only ever behave in the same way as they would in the guess potential if that's the ground state. They might have dispersed more or even grouped closer together if it's not the correct one. So again, we try to guess the density, which is the ground state, the one that minimizes the energy. Sorry for the rant, but it is a key concept when we try to understand why the simulation we will run would eventually minimize the energy of the system. We will do this DFT simulation in Quantum Espresso, which is an open source computational chemistry software. There are even more details there are, as you could use specific atom types that alter the way energy behaves, but in general, to run a simulation of this kind, you need the starting .c file, the atom files, and an input script. Then run it and wait for the structure to optimize. This would usually take around a week on most weaker server clusters. We did this for Gandhar's ZIF-62, which now has total force below 0.025 Rydberg per Bohr. For comparison, to convert this to something generally more meaningful to a wider audience, Rydberg per Bohr is converted into electron volts per angstrom. In other words, there is roughly 0.64 electron volts per angstrom of forces present in the system. This, averaged over the whole system of 320 atoms, would be 0.002 electron volts per angstrom of force acting on each atom. Now, this is a severe approximation. Quantum experts provides per atom forces data, but this comparison is to be taken only as a simple demonstration of the precision of the system. This is not as accurate as the models get, but with the available computational power, time, and the fact from now on we will not use quantum theory, it was sufficient. Now that we have our ZIF-62 optimized model, let's melt it and create a glass from it using molecular dynamics. At its core, MD, molecular dynamics, it is actually pretty simple. Instead of solving quantum equations, we treat atoms as classical particles and simulate how they move using Newton's laws of motion. For each atom, we essentially solve force equals mass times acceleration. The forces come from interactions between atoms, and once we know the forces, we can update positions and velocities step by step, typically in the order of femtoseconds. So MD gives us something DFT usually cannot: time evolution. We can literally watch how a material evolves, how bonds stretch, break, reform, and how structures changes under temperature or pressure. That's how we would create our glass. We can calculate these forces using ab initio, quantum mechanics, but that is too computationally expensive for a system that now would be 2560 atoms big. So instead of this, we use what are called force fields. A force field is essentially a mathematical model that approximates how atoms interact. It defines energies and forces using predefined equations for bonds, angles, and unbonded interactions. This makes simulations orders of magnitude faster than quantum methods, which is why MD becomes practical for large systems and long simulation times. However, most traditional force fields assume that bonds do not typically break or form, they are fixed. That's a problem for processes like melting, from where glass actually arises. This is where ReactFF comes in. ReactFF, or reactive force field, is designed to handle chemical reactions. It allows bonds to continuously form and break based on interatomic distances and local environments. Instead of fixed bonds, it uses bond orders that change dynamically during the simulation. We create glass in MD through a process called melt quench. We take a crystalline structure, heat it up to a very high temperature until it melts, meaning the long-range order is lost, and then rapidly cool it down. During the cooling, the atoms don't have enough time to reorganize into a crystal again, so they freeze into place into a disordered amorphous structure. That's how we simulate the formation of a glass. The important part here is that the final structure depends heavily on how we run this process: the heating rate, maximum temperature, cooling rate, and simulation time. A couple of years ago, a paper was published by Castell and Coulthard that tackles the chemical problems of melt quenching ZIF-4 using ReactFF, and noted how they got some improvement. We will build on that and provide a more optimal protocol for running these simulations. We did a total of 6 different simulations over the course of a few months, all with a goal in mind. Before any melting happens, however, every simulation goes through a preparation phase. The idea here is simple: bring the system from essentially zero temperature up to room temperature in a controlled way, so we don't introduce artificial stresses or instabilities. This is done gradually, first stabilizing at very low temperature, then slowly heating to 300 Kelvin, and finally equilibrating both temperature and pressure, so the structure is physically reasonable before we start modifying it. From that point onward, all simulations switch to the same goal: simulate melt quench, but under slightly different conditions. The first trial we did, called Castell-Coulthard, would act as the control. This is the standard ReactFF melt quench procedure that Castell and Coulthard deemed best for ZIF-4 in their paper and is widely used in literature. The system is heated stepwise up to 1100 Kelvin with equilibration pauses every 100 Kelvin, and then cooled down in the same controlled way. This method is considered reliable and is often used as a reference for comparison with more accurate quantum simulations. The second run, the 740 Kelvin run, tests a key question: does ReactFF behave better at low temperatures? Instead of going all the way to 1100, the system is only heated slightly above the experimental melting temperatures of ZIF-62. The heating is also slowed down near melting, and the system is held at that temperature for a longer time to allow proper structural rearrangement. This run checks whether a more physically realistic melting process leads to a better glass structure. The third run, the 1300 Kelvin run, pushes things in the opposite direction, however. By going to a much higher temperature, we test how sensitive the final structure is to overheating. This helps evaluate whether excessive energy introduces unrealistic bond breaking or structural damage. The fourth run, slower heating speed, focuses on another known issue: heating too quickly. Rapid temperature increase can cause non-physical bond breakage and distorted geometries, so here the heating rate is reduced to see if a slower transition improves structural accuracy. The fifth run, heat in pressure, explores something that is almost always ignored in most melt quench simulations: pressure. Most simulations are done in vacuum, but real materials really don't exist in vacuum, so here melting and quenching are performed at atmospheric pressure with careful control to avoid sudden force spikes. This allows us to evaluate how pressure affects the resulting glass. And finally, the sixth run, no equilibration, removes one critical step: the equilibration at intermediate temperatures. Instead of pausing every 100 Kelvin, the system is heated continuously. This run is essentially a stress test designed to show what happens when you skip equilibration, and why those pauses are actually essential for obtaining physically meaningful results. After melting and quenching, all systems are brought back to the same final conditions: 300 Kelvin and zero pressure, and undergo a long equilibration phase. This ensures that any remaining stresses relax and that final structures are stable enough for analysis. Having simulated all of these, we then evaluate their accuracy based on a few parameters. Firstly, their RDF, radial distribution function of zinc nitrogen, which showed at what distances from the zinc was nitrogen the most likely to be found, how much of it and how it behaved at greater distances as the disorder in the system reaches roughly the ideal gas law. Also, their angle distribution of nitrogen-zinc-nitrogen complexes that display at what angle is the most probable for such structure to be in gas form. Here, we look for a higher peaks and lower dispersion. Their envelope density was also checked. We looked for values closest to reported from experimental trials. And finally, coordination of zinc-nitrogen with a cutoff at 2.3 angstroms, where we try to retain the greatest possible coordination, as in theory the best glass should have very high coordination in order for the ZIF to not lose its chemical properties. For a deeper understanding, we advise you to read the section of the paper, but in general we found this. A. Equilibration at every 100 Kelvin is a must. Without it, the structure becomes abysmal. B. Overheating must be prevented in all cases, as it performed the worst out of all trials. C. More time at molten state also resulted in greater angular dispersions. D. Lower heating speed meant a higher retention of coordination and less dispersed angles, and a better overall structure. And E. Pressure has little to no effect on AD and RDF wise, but retains higher coordination. Based on these conclusions, we deemed the slower heat speed run as the best in terms of accuracy, efficiency, and actually displaying what would happen in real life. So we used it in the final computational chemistry part, which is the CO2 adsorption comparison between crystal and glass. To evaluate how ZIF-62 actually performs in practice, we moved to adsorption simulations using Grand Canonical Monte Carlo, or GCMC. The idea behind GCMC is different from molecular dynamics. In MD, we track how atoms move over time. In GCMC, instead, we simulate how many gas molecules enter and leave a material at fixed temperature, volume, and chemical potential, which is directly related to pressure. So rather than solving equations of motion, GCMC works by randomly inserting, removing, and moving molecules inside the structure and accepting or rejecting those moves based on probability. Over many iterations, this builds up a statistical picture of how much gas the material can absorb at a given pressure. This makes it ideal for modeling adsorption isotherms, essentially how much CO2 a material captures as pressure increases. Now, applying this to both crystalline and glassy ZIF-62, we can directly compare their performance. The first major result is straightforward. Both follow a similar trend, but the crystal consistently absorbs significantly more CO2 than the glass. The reason is structural. The crystalline MOF has a much larger accessible pore volume, which gives more space for gas molecules to occupy. In other words, pore size is the dominant factor. What's more interesting is the shape of the adsorption curve. For ZIF-62, the uptake increases rapidly at low pressures and then gradually levels off towards saturation. This is not a simple linear behavior, and it highlights something important. ZIF-62 performs particularly well at low pressures. This makes it especially relevant for applications like passive carbon capture, where CO2 concentrations are relatively low. Quantitatively, the crystalline ZIF-62 saturates at around 5 atmospheres, reaching roughly 50 cubic centimeters of CO2 per gram of framework, which is about 0.1 grams of CO2 per gram of material. So, roughly speaking, capturing 1 kilogram of CO2 would require about 10 kilograms of ZIF-62. That may sound large, but because the material is reusable after activation, it can cycle repeatedly and capture much more over time. Compared to other well-known MOFs like ZIF-8, ZIF-62 performs significantly better at low pressures. At around 1 bar, ZIF-62 absorbs roughly 4 times more CO2. At higher pressures, ZIF-8 catches up, but for real-world, low-pressure capture scenarios, ZIF-62 has a clear advantage. Now, compare crystal to glass, the difference is visually quite large when measured per mass. The crystal clearly dominates. However, when normalized by volume, the gap becomes smaller, though still significant. At higher pressures, the crystal still outperforms the glass, but not by an order of magnitude, more like a factor just under 2. So overall, the takeaway is quite clear. Amorphous ZIF-62 does not offer a chemical advantage for CO2 absorption. Its performance is consistently lower due to reduced pore accessibility. Its potential lies more in processing and shaping advantages, for example, easier handling or forming into solid filters, rather than raw adsorption performance. For adsorption alone, the crystalline form remains the better choice. However, studies have shown amorphous ZIF-62's potential in glass separation, so further simulations must be conducted to investigate that application. As if it has a great performance, amorphous glass made from MOFs may carve its way into industrial filtration systems and biological carbon recapture.
After all the chemistry and analysis, we go to the industrial part. Why does this matter? The problem we're trying to address is industrial carbon dioxide emissions. Large stationary sources like power plants, cement kilns, and steel production, as well as chemical manufacturing, release enormous volumes of CO2 every day. Unlike transportation emissions, these gases live through a single exhaust system, which makes them ideal target for capture, or at least in theory. Modern carbon capture approaches already exist, but each of these comes with major trade-offs. Amine scrubbing systems chemically absorb CO2 very effectively, but generating the solvent requires large amounts of heat and energy. Cryogenic separation works well at scale, but it's extremely energy intensive. Polymer membranes are cheaper and modular, yet they usually suffer from the fundamental limitations, including increasing gas flow, reduced selectivity, meaning efficiency drops. This is where materials like AG ZIF-62 glass membranes become interesting. Instead of chemically binding carbon dioxide, these materials separate gases through molecular scale sieving. These amorphous glass structures lack grain boundaries, creating uniform diffusion pathways where CO2 passes preferably over nitrogen and oxygen. In principle, this allows faster separation without sacrificing selectivity, something conventional membranes struggle to achieve. The system proposed here combines that material with biological carbon utilization rather than simple storage. The process begins at the emission source. Raw flow gas cannot go directly into advanced membranes, so it first passes through conditioning stages. Particle filters remove ash and soot, chemical scrubbers capture acidic gases, which will damage algae, and cooling plus drying removes moisture that would otherwise block membrane pores. Many individual industrial facilities already operate similar systems for environmental compliance, meaning this step expands existing infrastructure rather than replacing it. The clean gas then enters modular separation units containing hollow AgZif-62 membrane tubes. Gas flows through the pressurized interior, where turbines generate a low-pressure region outside the membranes. Carbon dioxide preferably diffuses through the membrane walls, creating a CO2-enriched stream. Multiple modules operate in parallel and series, so separation continues even during maintenance, gradually increasing CO2 purity with each stage. Instead of compressing the captured gas for undergoing storage, the design buffers it in storage tanks and redirects it into a biological utilization stage, essentially a controlled spirulina cultivation system. Spirulina, a photosynthetic cyanobacterium, consumes carbon dioxide efficiently, tolerates high alkalinity that suppresses contamination, and produces valuable biomass used in foods, feeds, and biotechnology. CO2 is bubbled directly to the culture, simultaneously feeding photosynthesis and circling the reactor. Sunlight drives most of the energy inputs, while solar-powered lamps extend productivity during poor weather or nighttime operation. The controlled carbon is therefore converted into living biomass rather than waste. After harvesting, the biomass can be produced into nutritional products or thermodynamically converted into fuels or stable carbon materials, extending the carbon resilience time with the industrial cycle. Economically, the system works because several value streams overlap: reduced emission penalties, potential carbon credits, sellable biomass, oxygen generation, and modular scalability. Instead of carbon capture being produced at a cost, it becomes part of the production process. Finally, if one wanted to remove carbon from the short carbon cycle and enter it into the long carbon cycle by putting it back into the earth, the spirulina can go into a pyrolysis reactor where it burns without oxygen and produces coal, a bit of ash, natural gas, as well as some biofuels. Thus, the project circles from chemistry into analytical chemistry, simulations, industrial design, and finally into ecology. Thank you for watching, and see you next time.